entire screen. Okay. Can you see my screen now?
Yes.
Okay, yeah, cool. So I will just wait like this. Is it okay?
Yes, yes. Please
Okay.
wait for a couple of minutes and
Yes, yes.
we'll just allow others to join.
Okay. Cool.
Yeah. Thaw, can you unmute yourself, please, again?
Uh, okay, I unmuted it.
Okay. Yeah, we just muted everybody to restrict the. And also, you can share your presentation now.
Okay. Can you see it now?
Yes, it's coming. All right.
Okay. Okay.
So, hello, welcome everyone again for our this session. And this session will start with two training programs, and then after that, we'll continue with the contributory talks from our participants. So, for the first training session, I welcome Mr. Thaw Tar, Dr. Thaw Tar, and he will be speaking today on the tips and tricks for working with snappyHexMesh. Thaw has earned his doctorate from Osaka University, and he is now a research engineer in Hitachi. And he is also running his own CFD initiative called CFD Monkey. So I think he will talk about it. He's a very active contributor of OpenFOAM knowledge promotion. So thank you, Thaw, for accepting our invitation, and we are looking forward to your talk. You can start now.
Okay. Uh, Thank you, Dr. Bose, for this very valuable opportunity, and I am very happy to share what my experience. Okay, my topic is tips and tricks for working with snappyHexMesh. So everybody knows snappyHexMesh because it's like the most popular mesh generation tool for OpenFOAM, and I will share some insights during from my experience to make this snappy hex mesh for to make to give you better results. So the
Bob, can you
disclaimer.
make it full screen, please? Your
Oh,
slides.
okay. I will. Okay, I will now go in full screen. Can you see it now?
Yes, perfect.
Okay. So this offering is not approved or endorsed by OpenCFD. Okay, I skip it. So the training session target. After this training, you will be able to generate a high quality open form mesh like this. So is this mesh really good or is high quality? So what is a good mesh? A good mesh, according to my definition, must be able to provide robust and accurate solutions with minimal number of elements. So by means of robust, I want my simulations to be very stable with no divergence and no strange oscillations. And by means of accurate, I want to use second order numerical schemes for my major flow variables, except the turbulence variables. For like velocity, pressure, etc. I want to use second order uh, numerical schemes for accuracy and with minimal number of elements. And your mesh should be fine enough in important areas to resolve the flow features in the area in these areas, while coarse enough for your computer to run readily. Yesterday, I heard that Professor Nielsen's mesh could like take 40 years if you are on a single core computer. So, but I am a lower level, so I am a minimalist. Okay, so the mesh quality matrices for the mesh. My definition is your mesh should be clear of errors during check mesh if possible. But honestly, I may not care much about a couple of skew phases with marginal skewness. So these okay, um, these are the check mesh original definitions: non-orthogonality less than 70, skewness less than 4, and aspect ratio it is like 1,000. But according to my experience, non-orthogonality until 85 it's manageable. Skewness until 5 or 6 it's very manageable. You can do sacrifice a little bit of accuracy, but your simulation will run very happily. Okay, for aspect ratio, there's no limit because if you are using serious resistance analysis on your, for example, aerodynamics, or I'm a ship guy, so if I do ship hydrodynamics, and if you are really serious about your y plus, like y plus around 1, your uh, aspect ratios inside your boundary layer mesh will be like 10,000 or like more than 10,000 is just natural. So snappy hex mesh will sorry check mesh will complain, but you can just neglect it as long as these very long aspect ratio cells are inside your boundary layer and inside your uh, regions where your gradients are large. I will not care. Okay, but the important thing is no strange cells or phases. For example, wrong oriented phases or some non-manifold points may crash your simulations. You need to be careful about this. These above things you can manage by using numerical schemes, but these strange cells are serious problem, which are sometimes harder to manage. Okay. Other than quantitative matrices, your mesh should be pleasing to your eye. So your eye is a de facto standard for meshing. If you see some rough edges or rough points, faces, you probably should uh, do the refine your mesh, or maybe you should remesh again. Okay. So Snappy Hex Mesh. Snappy Hex Mesh is a hex dominant unstructured mesh generator in OpenFOAM for generating meshes of complex geometries. I wanted this session to be very basic. I mean, very beginner friendly, and so I will explain like these details, very basic things, as much as I can. Okay, so a lot of people think that Snappy Hex Mesh is not good enough for mesh generation. However, with proper knowledge and experience, you can generate really high quality meshes suitable for your own problem most of the time. There are sometimes it's really difficult, but other times you will be very you will be doing very good with Snappy Hex Mesh. Okay, so this is the OpenFOAM meshing workflow using Snappy Hex Mesh. So I have the numbers. First, you will need your background mesh, which is mostly Cartesian, and you will mostly like use block mesh to generate this. And you can also use like other uh, hexahedral structural meshes generated either by block mesh or other softwares like Salome and Hex Blocker, or pointwise, or if maybe ANSYS ISM, some sort of hexaheterostructure mesh will be fine for your background mesh. Okay, but most of the time, like 99% of the time, you will be using block mesh. Okay, and then you will need your geometry. You can create your geometry inside Salome. I use Shaper daily, and you can clean your geometry if you got that geometry from somebody, or in some sort of CAD formats like STEP or IGS, etc. You can do the cleaning and creating your uh, geometry for your in Salome. After that, you may want to create the surface mesh, STL. Actually, you can just export inside your CAD geometry as an STL, but it might not be good. So you may want to um, remesh that STL again for your purpose, and you can do this in directly mesh in Salome. We can you call it triangulation. You can do the triangulation in Salome. After that, where we have the block mesh and we have our STL, and we can generate our snappyHex OpenFOAM mesh in snappyHexMesh. Okay, so snappyHexMesh has three main steps. The first one is the castellated mesh, the second one snapping, and third one add layers. So this is the fundamental workflow for snappyHexMesh, how snappyHexMesh works. So you have your background domain, and you have your STL surface, and by using block mesh, you will generate the grid background Cartesian grid, uh, and you will also have the STL, and these the grid lines will cross your STL surface at several points. And what snappyHexMesh does is it will create split the cells uh, on these surfaces, as we can see here, and it will remove the cells unnecessary for your mesh. So it will decide whether you define your location of mesh is inside around here or inside your STL. If you define your location in mesh as inside your STL, all you have will be your STL as a mesh, as a volume mesh. And so may want to make sure your location in mesh is good. And after that, it will smoothen these very rough cells uh, by comparing with the your STL file, and it's called snapping. And then finally, it will shrink your mesh around your STL, and it will try to increase add the layers near the your STL. So this step is called add layer step. So here are the tips. So I will provide three main tips. Have a good background mesh, have a good STL surface mesh, and have a proper snappy hex mesh dict. And the first one is a good background mesh. You want your background mesh to have aspect ratio of around 1. And your block mesh should be fine enough to cut the STL properly. We want to make sure that your block mesh grids cross the STL more than once in each direction, and if necessary, you can locally refine your block mesh. A good example is the DTC Hall tutorial in multiphase interforms and areas. It will show how to start with a very coarse block mesh and how to refine only near your STL surface. Okay, I recommend you to have a look if you are interested in such problems, like in hydrodynamics or something like this. For aerodynamics, people maybe not useful. Okay, so and edges in your STL file should be aligned with your background mesh as much as possible. It will give you a good uh, life, happy time with snappyHexMesh. And so for your background mesh, pro tip is an Excel sheet. An Excel sheet can save you a lot of time. So, oops. Oh, let me demonstrate a little bit. And this is my Excel sheet. And of course, the geometry is the armored body. And I input the dimensions for my geometry here, and it will calculate the domain size and consequently the input for my block mesh. So my block mesh should be from here to here. And if I input the number of cells around my geometry STL file uh, next to my STL file, uh, I just added 100 cells. I want 100 cells in this direction, closing to my geometry. So I can get the number of elements in I need to set for my block mesh, provided that I have 4 levels of refinement during snappyHexMesh. Okay, now I have the uh, domain size for my block mesh, and I have the number of element counts for each direction in my block mesh. So what I do is I will set these values directly to the block mesh, and here is the number of elements in each direction. And again, I want to make sure whether everything is okay. So this is my block mesh. Okay, and then here is the inside is my STL file, and by using slices, you can see, oops, here your my STL file is crossed by like 6 block mesh elements in X direction and like 3 elements in Y and Z direction respectively. You may think it's a bit coarse, yes, but it will do okay. Okay, and by having such an Excel sheet, you can also calculate the your nearer cell thickness, and you can also estimate your target y plus values by if you use this mesh. So I can make sure that my y plus is around 60, so I can use wall functions and I am okay with it. Okay, let's go back to our presentation. And so the first one is have a background mesh. If the aspect ratio is too large, you will have uneven refinement phases like this, and consequently, you will have skewness, a lot of skewness. And by using a better background mesh with aspect ratio around 1, you will have a much better surface refinement mesh with no skewness. Your skewness will gone. And another tip is if you are modeling a cylindrical object like a propeller, impeller, or something like this, you may consider using a cylindrical background mesh. I mean the O-grid, and it will give you less skew cells, less cell count, and better mesh quality matrices. Okay. Oops. Okay. Now next step is to have a good SDL surface mesh. And the first one is to keep your geometry clean and smooth. It's a lot of work. You need to remove bad edges or faces and clean your geometry. If it is generated by some other CAD software or some other CAD designers, you will need a lot of time to do that. But I will not cover it. And after that, you may need to refine your SDL surface and surface orient the normal faces. And finally, may want to use the surface check. Okay, I will explain this soon. So again, this is our uh, OpenFOAM meshing flow. We have now block mesh, and I will show you how to generate this. Okay, now this is Salome, and I created this geometry by myself, so there is no cleaning necessary. And I can create a surface mesh here in Salome, and by using these triangle manifesto and wire discretization. These schemes are will really robust and will give you enough refinement in most of the regions. And you can just export it here, your SEL mesh, and I will not export. So your exported mesh will should look like this, okay? But actually I will explain later. But your exported STL need to should look like this, okay? But if you export it from your cat module, like here, you can also export. You can here you there's an export option. Your mesh, your STL will be like this, okay? And there are so many coarse triangles and so many um, long and skew triangles, which snappyHexMesh sometimes have difficulties. It's not all the time, but sometimes. But so you may always want to remesh, triangulate your geometry before exporting your STL. But when if you only have the STL like this, and you don't have the access to your geometry, you need to remesh this. And one of the tools is MeshLab. MeshLab is a good open source tool to deal with these STLs. You can smoothen, clean up, and repair your STL file in your MeshLab, and we will use remeshing capabilities in here. So what we have is our mesh, a directly exported STL mesh here, this guy, and we want to remesh. So you can click filters, remeshing, and another remeshing. So this will lead to isotropic explicit remeshing, something called like this. And here you may want to set the target length to be around 0.5. I found it from my experience is a sweet spot. Okay, just apply and okay, here we go. We just remeshed the geometry, the STL from our normal exported STL to this much better STL. So you can just export the mesh as STL. Okay, so this is the before and this is the after. Just one click in Meshlow. Okay, and finally, we need to surface orient. There are times when the surface normal vectors for your STL file are not oriented well. It can badly affect snappyHexMesh output. It is worse than the previous uneven STL. You, you should always do this, and it will help you snappyHexMesh a lot. Okay, so what it does is STL surface has the normal vectors, and sometimes these normal vectors are uh, uh, directing inward inside your STL. It should always be pointing outward. It If it's inward, like the left figure, you have problem. Okay, and so or if you all you need to do is use surface orient and your input STL and output STL, and you want to give it a really large number, and you will have a reoriented mesh easily with the normal vectors or much better. Okay, and next, you want your STL to be good for meshing. It means it has no illegal triangles and it has surface is closed and watertight. Otherwise, snappyHexMesh will struggle a lot of times. So the command is to use a surface check and your STL file name, and you need to check whether it has no illegal triangles and whether the surface is closed. You need to check these two, and it will give you a lot of better results than not. Okay, finally, well, we need to edit the snappyHexMesh dict. SnappyHexMesh is a very powerful tool, but it has too many parameters to adjust in order to obtain a good mesh. Okay, so this parameter search is generally an iterative process. You need patience, then you need to do trial and error a bit. However, these tips will ease this process. So the first tip about snappyHexMesh dict is mesh each step. As we mentioned, snappyHexMesh has three major steps: constellation, snapping, and adding layers. And for very fine meshes, each step takes a lot of time. Okay, so therefore it's more efficient to fine tune each step before moving on next step, and you make sure you are satisfied with the result. Okay, so especially for very complex geometries with a very large number of cells, snapping and layer additions may take much more time than constellation because they are iterative, very iterative, and they need to relax the mesh all the time. So by using carrying out only constellation first, you will have the idea on the cell count and refinement regions after this constellation. If you're not satisfied with either of these, you can adjust your refinement parameters and it will save you tons of time. So this is what each step looks like. So you have after the castellated mesh, you will have this very rough mesh, but you will have the idea of whether your refinements are occurring. And if you are not happy with this, you can just increase the refinement parameters or decrease the refinement parameters. Okay, after that you snap the mesh, and if you have bad say bad phases or rough phases, you may want to adjust your relaxation parameters and snapping, and after that you can move on to layer addition, etc. Okay, so next tip is you should consider setting the number of cells between each refinement. Some people call buffer cells, buffer layer between each refinement steps. So you want to set at least 3 to 5. Even 10 is a good number if you can manage it, but it will add a lot of cells to your mesh. Okay, especially helps you with a region of large gradients such as separations, areas, and wicks. If there are sharp changes inside the flow field during visualization, so you just use your coarse mesh and just run the simulation and visualize it. And if there are sharp changes inside your flow field, you may want to increase the number of the cells numbers between levels. Okay, so what is look like? The leftmost is the one cell between each refinement, and you can see here the cells from very fine to coarse just coarsen very rapidly. So it's not good, especially if you are flow variables change rapidly. For example, well, you have so much gradients, and you want to make sure gradually change. So 5 cells is the middle, and if you put 10 cells between each layers, each refinement is like the last part. Okay, and another tip is you can use ParaView to visualize even before doing any snapping. So you can create boxes, cylinders, and spheres inside ParaView to visualize the location and range for your refinement regions. And then you can use their coordinates inside the snappyHexMesh directly. It will save you a lot of time. For example, okay, I'm not sure I still have that much time. Okay. Here is the refinement box I just created in ParaView. It's small, but you can just check the bounds for its dimensions and its coordinates, and you can just set these values inside your snappyHexMesh as a refinement box. So it will give you an idea of how much your refinement regions are. Okay. Again, you can use the same trick to use ParaView and to check the location inside your mesh. It's especially useful for internal flow problems where you cannot exactly know the inside location of your geometry readily. For external flow problems, it's easier, but for internal flow problems with complex geometries, you may want to use Prabir to visualize your location inside your mesh. And the last one is a little bit advanced. In there, you may want to turn off relative sizes if necessary. And if you turn on, snappyHexMesh will use the size of the nearest cell, the wall, as a reference thickness for your boundary layer mesh. If turned off, it will use absolute values. For example, if you define the surface refinement of your wall patch with a refinement range like 4 to 6, your cell size, patch will be different. And consequently, the number of the prism layer thickness will also be different if you turn on relative sizes. It's good sometimes, and it's not good sometimes. So because it will give you very uneven boundary layer mesh, which may want to like it or not. But if you turn the relative sizes off, it gives you much more control, because you need to input the absolute values of your boundary layer thickness. But it also comes with much more responsibility. You need to calculate the final thickness of your boundary layer mesh and input it precisely. As you can see here, I calculated wrongly, so my boundary layer mesh is a little bit too thin. Okay, but on the other hand, computing Y plus is much easier. If you turn off relative sizes. Okay, this is
Oh,
the
can you
summary.
please conclude?
Yes,
We are
I'm
actually
concluding.
towards the end.
Okay.
Yes.
Oh, okay. So snappyHexMesh is a very powerful tool, but you need to be rigorous with your block mesh, STL file, and snappyHexMesh settings in order to obtain a high quality meshes for your high fidelity OpenFOAM simulations. And you can download all the training materials in this link. I will also provide through the chat. And you can have any question, you can also contact me through these emails, and the softwares I use are here. Okay, thank you very much.
I think we didn't see your last slide with your contact
Okay.
details.
Oh yes,
But
okay.
thank you very much, Thaw. I mean, it was really very helpful for the beginners. So I request you to please go through the chats. There are a few relevant questions which you can probably answer in the chat itself. But due to the constraint of time, we will move forward with the next training. So you
Okay.
can type in the chat box and answer to the queries. Thank you
Okay.
very much. It was
Thank
really
you very much.
helpful.
Yes.
And we have recorded the session, so we will share it with everybody. Thank
Okay.
you.
Cool. Thank you very much.
So can I now request John, our next speaker for the training session 3 on heat transfer simulation, uh, to actually share the screen to see if there is any problem.
Hello, sir. Can you hear me?
Yes, we can see your screen and also can hear you. Right. Yeah. So before John starts his presentation on the training session on heat transfer simulation, let me briefly introduce him. So Mr. John Pinto is a senior PhD scholar in IIT Bombay, and he's a very active contributor to the FOSSEE project. And he delivers different trainings in the workshops organized together with FOSSEE. And so thanks, John, for accepting the invite to deliver this training, and we are looking forward to it. So, yes, you can make it full screen and start.
Yes. Thank you, sir. Thank you for this opportunity. Hello, everyone. So I will briefly start with introducing you to heat transfer simulations. So I've planned this for beginners. So maybe this content will be little slow, and we'll do some simple problems in this. So what is the outline? So first I'll be discussing the energy equation, what OpenFOAM solves. I had also included a conduction simulation case, but I will first go to the forced convection simulation case, and if time permits, I will do the conduction simulation case. Okay. So we all know that there are three modes of heat transfer. conduction, convection, and radiation. In conduction, the molecular diffusion is the what you can say the mode of heat transfer. In convection, it is diffusion plus the bulk motion of the fluid particles. And radiation is a mode of heat transfer in which there is no medium. So we'll try to see how all of these are added in OpenFOAM. So OpenFOAM solves the total energy equation which I have given over here. Okay. So total energy is the sum of thermal energy plus mechanical energy, where mechanical energy is further subdivided into kinetic energy, potential energy, and also the strain energy. So this equation, once simplified, the final form can either be expressed in terms of the internal energy or the enthalpy equation. Okay? Now, if you want to go into the derivation of this, I would refer you to this this document on CFD Direct. It gives you all the information, and they have also mentioned why total energy equation needs to be solved. I will briefly tell you, say in specific cases where, for high speed flows where you will also observe shock, that time the temperature will not be predicted well if you don't take into account these terms, the strain contributions. So for that case, the total energy equation is solved in OpenFOAM. Now, how does this relate to conduction, convection, and diffusion? What we basically know. So if you look at this term over here, this term is nothing but our advection term, and this term is nothing but our what you can say diffusion term. So this will solve the conduction. Diffusion with advection together will solve the convection. Now radiation is if we have to solve, we need to include that as a source term, where this rho and r is a source term. But since this is a beginner thing, we will not be entering into radiation. We will only look at conduction and convection heat transfer. So what are the heat transfer solvers available? So the most used solvers are buoyant pimple foam, buoyant simple foam, and CST multi-region foam. I have listed what they do. So buoyant simple foam is a transient solver. Buoyant pimple foam is a steady state solver. It also has the possibility to use radiation heat transfer as well. CST multi-region foam is a more versatile solver in which you can solve for both turbulent heat transfer as well as radiation as well as conjugate heat transfer. Now this solver will be useful, say if you want to simulate something like CPU heat sink cooling, where the heat is flowing from the CPU to the heat sink material through the fins and to the fluid. So if you want to analyze the heat transfer from the solid to the fluid and you want to simulate both the solid and fluid regions, then you should go for the CST multi-region foam. Now, for the present demonstration, I will be showing the buoyant simple foam case. So in this case, this is the general case folder structure for the buoyant simple foam case. This case structure can become more complex if we add turbulence parameters, and all those also will come in. But this is a simplified version of that. Okay, so now what type of energy equation is solved in buoyant simple foam? So if you see, I have taken a snippet from the source code of the buoyant simple foam. Here it gives the user the option to choose whether the user wants to use enthalpy or internal energy for calculation. Now this 1, 2, 3 are the terms which I've highlighted over here. Now since buoyant simple foam is a steady state solver, all these transient terms will drop off. Okay. Now also this strain energy contribution will drop off because these are low speed flows, and the contribution from this will be very insignificant. Now this solver very what you can say in a simple way, it combines both the equations. So here if you see, this is the first term that is being solved. Now for the second, the first term is similar for both internal energy as well as enthalpy. Only the second term is different. So that is where an if-else statement is added. So if the what I can say user specifies internal energy, then the first term gets solved. That is this. That is the combination of these two. Otherwise, that means if the user has specified enthalpy, then the second term, that is this 2H term, gets solved. Okay. Then the third term is the diffusion term. Fourth term is the rho UG, that is the potential energy term, and the fifth term is the source. So now you can add source specific to your requirement, and also radiation can be added depending upon the requirement. So this is what the energy equation in buoyant simple foam looks like. Now the problem that we have today is convection through a heated pipe. So how it has been set up is that we have given a uniform velocity at the inlet through the pipe, and we allow the flow to develop. So there is certain developing length, and once the flow becomes fully developed, we give a heated section. Now the various dimensions for the geometry have been listed over here. So we are saying that the Reynolds number for this is 500. So the flow is laminar. Based on that, I have calculated what will be the entrance length. So entrance length is 3 meters. So I have set the L1 and L2 to be 3.5 and 1.5 respectively. And all the velocities and the properties of the working fluid are listed over here. So now this is the folder structure that I've talked to you about. Now I will briefly go over them one by one. First will be the block mesh dict. So now the flow through a pipe, we can do a full pipe simulation that is available on our FOSSEE website, where we have done flow simulation through a pipe. But also it can be solved as an axisymmetric case. So to solve it as an axisymmetric case, we need to set it up as a wedge type of a geometry. This. Now, for axisymmetric case, the requirement is that the wedge angle should be less than 5 degrees, and there should be only one cell running in the azimuthal direction, that is between the wedge faces. Also, in this case, because we have one unheated length and then the other heated length, so we are using two blocks in block mesh to define this. Okay, and these are the two wedge faces on the side. So as far as boundary conditions is concerned, we have the 0 folder, the PRGH, T and P folder. So what is different over here is that we are not just solving for P, we are solving for PRGH. That is pressure without the hydrostatic component. Now this formulation comes in handy for flows like say buoyancy driven flows where density changes, or maybe multi-phase flow where density changes are significant. So in such cases, PRGH pressure is used to is solved, which is much more convenient to be solved. And the other is that specifying PRGH PRGH pressure simplifies the complexity in specifying the pressure boundary condition if there is hydrostatic variation. So if you remove the hydrostatic, like if I say if there is a horizontal wall, the pressure due to hydrostatic component will be pressure will be higher at the bottom and lower at the top, right? So that hydrostatic component, when it is removed, we can get a constant pressure, and that specification will be much easier. So here I have summarized all the boundary conditions tabulated. Now let's look at them one by one. So for the inlet, for PRGH, we are specifying here a fixed flux pressure boundary condition. Now this is something like similar to a zero gradient boundary condition, but it adjusts the gradient depending upon the body forces that are present. Now at the outlet, we have given PRGH pressure value of 0. For the temperature files, for the adiabatic section, we have given a 0 gradient because we want for the adiabatic section there should be no heat transfer. So for that, for the boundary to be insulated according to say Fourier's law, for Q to be 0, your dt by dx should be 0. So that's why our gradient is 0 over there. So this what you can say is similar to a adiabatic condition. Now for the heated pipe, what we want to give is a heat flux boundary condition. So again, if we look at the Fourier's law, Q is equal to K times dt by dx, right? So then dt by dx will be nothing but Q by K. So our heat flux is 20 and our thermal conductivity is 0.0242. So based on that, we have calculated a gradient and given a fixed gradient to the pipe. So this simulates the heat flux boundary condition. Now for the other two faces which are wedge, for them, the wedge type of a boundary condition has to be given. Now, in this specific case, we have ignored gravity because this is a forced convection flow. Gravity effect will be negligible, so you need not include it. What is important is that we need to specify the thermophysical properties. Now, this thermotype specifies the thermophysical properties. Let's look at that. So first is what is the type of the thermophysical model. We are saying that over here, this is based on enthalpy, internal energy, and the calculations are based on density. This is what the first thing means. Second is what we are saying is the mixture is a pure mixture. That means there is going to be no reaction and the composition will be constant. Then transport is constant. In this specific case, I have given a constant transport property. That means it assumes the viscosity and the thermal diffusivity to be constant. In place of this, you can also use variable temperature or such type of a thing wherein you specify a polynomial that is dependent on temperature, or we give some equations. So if you want to know what type of options are available, one cool trick will be that in place of this, you just write something that is garbage. Like you may write something like banana. So then when you run the code, that time OpenFOAM will throw an error saying that this is not a valid option. The valid options are, and it will give you a list of what are the valid options. Then you can read through them and see which one suits best your requirement. Okay. Now the last is H constant for the thermo. That means we are saying that the CP and heat of fusion are constant. Now equation of state, here I've used a constant density. If you're solving buoyancy driven flow, you can use Boussinesq or you can use an ideal gas, something like that. And in species, we can specify what is the composition, the like the number of moles and molecular weight of each constituent. Now here this is where this is important. So energy, here for energy we are saying sensible internal energy. That means we are saying that solve the E equation, and because we are saying sensible, it is not considering the heat of formation. Okay. Now if you would have written sensible enthalpy, then it would have solved the enthalpy equation. Now for the mixture, we have here given that the molecular weight, because we are considering air, the molecular weight is 28.9. The density we have specified, the thermodynamic properties, and the diffusivity as it was given earlier, those values have been specified. Now how to run this what you can say case, you need to do first meshing, then do buoyant simple foam and parafoam. I have already run this case. So I will directly go to that case. Okay. Since I've already run, I can load the simulation results. So here you see the wedge type of geometry. I will first look at, say, velocity. If I go to the last time step and rescale it, this is what a velocity looks like. So what we can do is we can create a radial plot. So this will be plot along the y-axis. If I plot along the y-axis and I want to plot it close to my outlet, say like 4.9 meters, because the total length is 5 meters. And if I apply, I will get the various things. So here, let us first look at our say now the green one is our temperature. So if you see, first let us look at the temperature. The temperature, this is our axis, this is the radial distance. Okay. So our temperature is lowest at the center and highest at the wall, because the wall is getting heated. So we are getting a variation. Now if you see, this is only one half of the variation because we are solving the wedge. If you reflect it, you will get the full thing. Now if I want to see the velocity, I have unchecked the temperature and I've got the velocity. This is what the velocity looks like. Velocity will be highest at the center. That will be a Umax, and 0 at the wall. So this is very coarse because I've used a coarse mesh because I thought we will be doing a hands-on, so it should run quickly. But then you can refine, you can add more number of cells and refine and get a more accurate result as well. I will just close this. Okay. Yeah, going back. So this is the result that I've showed you, right? Now this, you can also validate this with our, what you can say, parabolic velocity profile. So see, this is a theoretical and OpenFOAM comparison, and we are very close. If we add more cells, it will be much more closer. Okay, now I think this was it for convection. I'll quickly switch over to the conduction case. So for the conduction case, the example that I have chosen over here is for the use of Laplacian form, because in conduction there is no advection and all, so we can use the simplified form, and it is like solving a scalar itself, like the T equation. So a physical 1D one-dimensional equation for 1D conduction, this is what typically we see in our textbooks. If I bring out my pointer, this is the typical temperature equation for 1D conduction with a heat generation that we see in our textbooks. So how this is coded in OpenFOAM, if you look at the Laplacian form case, we see over here, first term FBM ddt of t and Laplacian dtt, this is the second term, and the sources are modeled by the FV models. FV model handles the source. So if we look at this equation, our source is volumetric heat generation divided by rho and Cp. Okay, that means our source will have a unit of, I think, yeah, Kelvin per second. So this is our setup. So the setup that I'm going to show is that what we are saying is that there is a copper rod in which the two ends are maintained at 0 degrees Celsius, and I am adding heat. The heat source, volumetric heat source is 1e6 watt per meter square, and all the other values are realistic values for copper. So from that, the source term is calculated to be 0.29. Okay. Now, meshing for this is very straightforward. It will be just one block, and for that one block, for the two ends, so there will be two faces, 0, 0473 and 2651. These two faces are the ones for which we will be specifying the temperature. The other faces, because we are solving only in one direction, will be empty, type empty. So I've only defined two faces over here, and default, the rest will go into the default patch, and that I've given as empty. Okay. So I can directly, maybe I have simulated that case, and I will show you that. Okay. So this is our boundary. Here we can see the mesh as well. So we have mesh only in one direction because this is a 1D problem. Now I can go into temperature. Now along with this, I can also show you the plot how the temperature varies. So I will be plotting along the x-axis the temperature. So here I've plotted. This is at 0 time instant because this is a transient solver. I think I should have 1 minute. I'm rescaling it for all time steps so that when we change, we also see change in the color. That is what I just did by this option rescale for all time steps. Now, if I plot over a line along the x-axis, I get a 0 temperature throughout. Okay. Now, what I can do is I can move forward in time. So you see, as soon as we are marching in time, we see with the heat generation inside, the temperature inside is rising. That is what we can see over here as well. If I slowly increase, my temperature is rising and the profile inside is becoming parabolic. And after say about 50 or 60 seconds, the change 50 time steps, the change becomes negligible. If I go to the final time step, this is the profile that I'm getting. Now, if I open my presentation, yeah, this is the final profile that I've got. This I have compared with the analytical solution given in Incropera, and we see that we have a very good match. So this is one way to validate your result. This also, one more thing that you can do in this is, maybe I will be sharing the case files also, that what you can do is maybe here we have kept both the ends at 0, maybe keep one end at a higher temperature, say maybe one end at 2 or 3 Kelvin, something like that, and then see where the central peak shifts. So this is also something that you can try. Okay. Anything else? Okay. So these are the things that you can try. I will share the case files with you. Now I think I will take some questions. Also, what I would like to say is on the first day, Professor Kannan had said that we have a lot of contents. So wherein already case studies have been solved. So you can refer to this website cfdfossee.in, on which there are multiple problems that are solved over here. Okay, so you can go over them, see what type of boundary conditions they have solved, what type of case setups are there, because each case is different and the boundary conditions will be different. And if you have some specific query in which you need help, you can always write to us at contact-cfd@fossee.in, and we'll try to get back to you on that. Yeah.
Okay. Thanks, John. It was very helpful. I think there are few questions.
Okay,
We
sir.
have 2 minutes to take some quick questions. So if you want, you can actually take some of them. Let me see. Um, so this is something. I don't see any heat transfer related question. Um,
Okay, sir. I will share the case files and this with you. So then maybe
Yes,
the
exactly.
students
So
can you
for
can
the
try them.
audience, the case files relating to these training sessions will be shared through the same channel from CCST. So I will share all the case folders, and then you will get a link to download it and try it. And so yeah, so let's move forward. And I
I have
think
one query, sir.
yes, please go ahead.
Uh, where to use the internal energy equation and where to use the enthalpy equation, sir?
Okay, so generally internal energy equation you will specifically use for solids. Okay, and it is also advisable that an internal energy equation you can use for fluids as well, which are low speed flows, and that internal energy equation is more stable in that cases. For high speed, then you might have to go to, I think, enthalpy equation. But internal energy equation specifically you have to use for solid, like in CHT. If you go to the default case, if you're solving tutorial cases, right? Go to CHT folder. There in the solid, always internal energy will be used. So you have to use internal energy for solids and also for low speed flows. It is much more
Okay,
stable.
whether for Bion driven flow also we can use the internal energy equation, right? Since it is low
Hello,
speed kind of thing.
hello. Yeah, correct. Hmm. And
Okay,
also,
fine.
as I mentioned, if the flow is buoyancy driven flow, then you need to specify the either it is Boussinesq approximation or ideal gas in the density model. That is something that
Oh,
you need to do. I think those type of case studies are also available on our FOSSEE website. You can go through them as well.
yeah, thank you, sir.
So Jayashree, do you want to
Okay.
go ahead? If not,
Please.
Can you hear me?
yes, please go ahead.
I want to
See,
ask
okay,
John.
one question. Yes. Okay,
I
I was
want
reading the
I
question.
am I want to model a heat conduction problem in a solid fuel. The fuel is combustible. Can I do it in a similar way? In the start, in a similar way, the same as the copper rod example.
So, but if it is combustible, that means you also want reaction to take place.
Yes. We have a heat source. The heat source provides heat to the fuel, and a small part of the fuel starts combusting. The heat
Okay.
transfer takes place, and feedback will also be there. Heat feedback will also be there.
Then if there is a combustion, then this solver will not be able to work. But maybe you can, take some idea from this case setup and then work on that. Because here, for combustion, there will be some additional equations that have to be solved.
Yes, true.
Okay. So are there such files available in the FOSSEE group? Can we access that?
If you see the completed case studies, right, you can just
Yes,
search
yes,
over there.
yes.
Means, search option is available with a keyword, so you can search. I don't,
Okay.
remember. Nothing comes to my mind, so I'm
Yes,
not.
Jayashree, please go through the case study link of FOSSEE website and see if there are any relevant projects. Okay. So for the interest of
Okay.
time, I cannot take all the
Okay.
questions face
Thank
to
you.
face.
Thank you.
So
Thank you for accepting my
thanks,
question. Thank
Jayashree.
you.
So all
For
the
Nasrat
people who
number,
have
there is.
raised their hand, can you please write your questions in the chat, please? And I will request John to go through that and reply to those queries. Sorry, we don't have time to take all of your questions. We have to move ahead.
Sure, sir.
So
I'll
I
try to answer to
request,
them.
yes, thanks, John. Thanks for
Okay.
your talk, and the training was really useful, I think. So please look into the questions and answer if appropriate. Okay.
Yes.
So I request now, Arata, if are you available? Could you please turn on your mic and video?
Yes, yes,
Okay.
I'm available.
Yes. So John, can you stop sharing your screen? Yes. So yes, please share your screen. Okay, so let's move ahead with the next session. And the next small session will be the talks from research scholars on different topics of their project using OpenFOAM. And our next speaker is Arhata Senapati. And she is a PhD scholar in IIT Kharagpur, working with Dr. Rajaram and Professor Arnab. So I request Arhata to go ahead and present her research. And one important thing is to mention, I was forgetting that the next talks in this session, because we are running behind the schedule, I request you to make it short and present it within 10 minutes if possible.
Yes, sir.
Thank you.
Thank you, sir. Thank you, sir, introducing me. My topic is on wobble and droplet collision cases. Using first, I'll show this using the interform on bubble collision cases and droplet collision cases. Then I'll talk to bubble and droplet collision cases, which is based on multi-phase. So in OpenFOAM, we do these things by three process. First is pre-processing, where we generate the geometry by using block mesh, snappyHexMesh, or otherwise we can just import our geometries from Salom, Blender, or ANSYS or any other softwares. So after that, we in our OpenFOAM there are folders who solves these methods. So incompressible, compressible, multi-phase methods. I'll give out my talk on multi-phase, and after that, all these visualization, all these results we can see through ParaView or any other softwares like GNUplot, Salome, or ANSYS, TakePlot. There are other softwares also. So my case, I am going to show my case through Interform, which is the solver used to solve two incompressible isothermal immersive fluids using QA method. And in OpenFOAM 10 version, they have already inbuilt adaptive remeshing, means only Interform code. If you are giving remesh dict file, refine mesh dict file, then it will automatically refine it. And also, I will show that what is the pro and con of the multi-phase interform in using three-phase modeling. It is also used to solve incompressible and isothermal immiscible fluids, and it also uses the viewer method. So in bubble doublet case folders, you have time zero folder, which contains pressure, velocity, and alpha properties. In constant folder, it has dynamic mass, gravity folder, momentum transfer, phase properties, and physical properties of air and water. Then in system folder, for the geometry, there is blockness file and control dict, which controls the timing of time step, right interval, end time, all those fixed time, comes under control dict. And decompose bar, which is used for the parallel running. And there are finite volume schemes, finite volume solutions. And in set field, we define the alpha properties areas or volumes. And also sometimes the bubble and droplet velocity could be given through set field file. So in this case, first I'm showing bubble coalescence. It can be drawn through interform because it only serves two phases. So first is conservation mass is solved, then conservation momentum. Here, rho m, the mixer density, controls these two phases. First is gas and liquid. These two phases can be combined through mixer density and mixer viscosity. And there is another term, continuum surface force term, which contains the sigma surface tension and the phase properties. And the VF equation is solved for each and every phases. So how the VF tracks its interface? First, we can see the middle block, which is 0.5, and 0.2, 0.5. This line, two lines can be averaged as 0.35, means 0.7 by 2, 0.35. And similarly, another surface is can be calculated as 0.65. So the difference is 0.3 and the baseline is 1. And in this way, a interface is created through VOF method. This is a geometric reconstruction method of the VOF. So in this way, the alpha properties means the droplet gates is safe or bubble gates is safe. So through interform, we try to validate our cases, Vaga and Weber and Kumar and Venka cases, which gives the similar results, approximately similar results. So in OpenFOAM also we studied the physics like when when a bubble moves, it creates a low pressure zone, and through is it attracts a bubble towards it, and we can see the in OpenFOAM the OX structures and the streamlines surrounding the bubble and droplet. Through OpenFOAM also interform server we found the Thaw Tar rings, and this paper is a published one, and we publish these cases like how the flower like ejection forms and the tornado forms. Then comes to like it is about bubble coalesces. Now coming to binary droplet cases where there are a lot of where we need lot of meshes for this droplet see the droplet phenomena. So in order to reduce the computational timing and the computational memory, I have used dynamic mesh refinement test cases where the library file is dynamic refine final volume mesh, and the define interval is 1. And as I am using the alpha oil or I can use the alpha water, so this is my field value. And I have used the lower refinement level of 0.001, means if the alpha properties is in between 0.001 or and 0.999, then within this area only get refined. Otherwise, it will left open for the uniform grid size. And if as I can see that on refinement level is 10. So if somebody has some in some cell, it will go beyond 10, it will not going to define it. The unrefined level should be below 10. So the next thing is that n buffer layers means between the uniform grid size and the refinement area grid size, there is completely sudden jump. In order to reduce that sudden jump, what OpenFOAM does is OpenFOAM creates some dummy cells so that the OA propagation will be smooth and it will not create any unphysical situations. And the maximum refinement term, what it defines is there one cell will be labeled 0, that will be uniform grid size. If it will be divided into four sizes of uniform sizes square blocks, then it will be labeled 2. And in every square block of label 1 will be further can be divided into 4 blocks, which will be labeled 2. And similarly, in level 3 also, one small square block of level 2 will be divided into 4 blocks. So in this way, I have chosen the maximum defined level 2, and maximum cell size of 4 lakhs means if my sizes exceeds these numbers, then the refinement will be stopped, and it will be the whatever the size will be overall size of my computational grid, it will be between these values only within this maximum cell value. And I have used the correct flux values means as I have added some more cells, so I needed some fluxes for those areas also. So based on this dynamic refinement level of 3, we have calculated these binary droplet collision cases. In first cases, we can see that coalescence happens and it comes to a uniform block. But in the second case, it gets divided into two droplets. So these validations also, we did some validation on interform server based on binary droplet collisions, and it quite well matches with the experimental results. And similarly, in a quantitative data also matches. So coming to a multi-phase model where 3 fluids are considered, like here in this case, bubble and droplet collision cases. So what happens is here, fluid in between 3 fluids, fluid 1, fluid 2, fluid 3, there is some triple point junction where you can see that there is a white space which can be filled by multi-phase interform. So we had some modifications where we can see now in second picture, the fluid 1 covers this white color area. So this is another sort of multi-fluid interform which can easily track now, which can give a physical result. So in order to like this is only applicable for OpenFOAM version 7. So in order to more validify that whether it can track this multi-phase model, carried the droplet spreading phenomena, where there is two fluids, fluid 1 and fluid 2. In between, there will be a droplet where these three fluids, fluid 1, fluid 2, and fluid 3, have same density and viscosity. There will be no gravitational effect. So what happens is that based on the surface tensions, like sigma 1 greater than the summation of sigma 2 3 and sigma 1 3, there will be spreading of the droplet in between fluid 1 and fluid 2. So we can see that time 40 second in multi-phase interform droplet is just standing there. It's like a floating droplet. But in case of multi-fluid interform, it got spread in between these two fluids. So multi-fluid interform is giving us a very good results than multi-phase interform. So based on that, also let's see how this multi-phase model works, because this is a conservation mass equation, and this conservation momentum equation in mixer density and mixer viscosity model, we have considered all these volume fraction fields and their corresponding density and viscosities. Similarly, in CSA in force balance, and we have considered the surface tensions and phase fractions. And in view of equation, each and every phase is means whatever the number of the phases, it can be calculated through alpha I fraction field. So here the main question is how the sigma is a which I have explained the previous slide, is the main carrying factor, which is considered as a spreading or levitation factor. So here in multi-phase interval, we can see that sigma is the only one equation, only one number that is used to calculate on this Navier-Stokes equation. But in multi-fluid interform, there is no sigma ij. There is a summation of sigma factors, like summation of 1 to summation 2 and summation 3 is all three is used to calculate the surface force factor. So in this governing equation helps us to find that whether it will be partially spread or just carried out like a float, like a droplet will float, or any triple bond junction contact points. Based on this multi-fluid interform result, we calculated these bubble and droplet collision cases and find some results. And also from our result, we found that when the droplet moves, it creates some jet-like structure, so it goes and interacts with the bubble. So one of paper is published in based on this studies. One of paper is published in chemical science, and another is in communication with PRF. Thank you.
Thanks, Sarada. Very nice talk. I request you to please see through the chat. If there are any questions, please reply in the chat box, and we move ahead to our next talk. Thank you very
Okay,
much.
thank you.
What
Thank you.
nice talk.
Yes.
So now can we request Nikitas to please turn on the mic and camera?
Hello.
Hello, Nikitas. Could you please share your screen to check if everything is fine?
Yes.
All right. Yeah, we can see your screen. So Nikitas is an undergrad student in the University of Edinburgh, and he did his master's project with me and Dr. Francesco. So please go ahead with your presentation.
Yep. So my thesis project was on the wave and wake-induced dynamics on remotely operated underwater vehicles, or ROVs. Basically, ROVs are underwater vehicles that are used in the offshore energy sector for inspection, maintenance, or decommissioning of engineering devices. And recent research showed that the ROVs that operate at shallow environments have higher wave disturbances and are more difficult to control, but they can be controlled by using linear wave theory to predict their motion and implement a model predictive control system. However, this doesn't is not true if there is a fixed structure near the ROV creating a wake. Therefore, the aim of this project was to study the dynamics of the ROV when there are waves and the fixed structure creating a wake. So the three objectives were to first simulate the system, second analyze the ROV at different operational conditions, and third try to implement an MPC controller for this new system. So the project started very simple by simulating simple laminar vortex shading using the FOSSEE solver, and it was observed that the lift and drag coefficients had a percentage difference with published results of less than 2%. So validating this simple case and moving on to the turbulent regime, where simple validation case was also conducted, but this time using the Struhal number instead of the lift coefficients, and the percentage difference with published results of 8.8% was achieved. So this is a schematic of the computational domain shown on the right. On the left, we have a 3D schematic of the system, but for the sake of computational power, instead of modeling it in 3 dimensions and two-phase flow, it was modeled as a 2D cross-section of a plane passing through the center of mass of the ROV, with the ROV having 2 degrees of freedom, one rotational and one linear. This was the mesh that was used, which is zoomed in here at the area of interest. And this is a dynamic mesh in order to be able to capture the motion of the ROV. So we have the overset mesh method was used. In this method, we have 2 meshes. The background mesh, which has the fixed cylinder or the fixed structure, and the overset mesh, which has the free ROV that allows to move. The green cells in this mesh are the boundaries of the overset mesh and are not, the flow field in those cells is not calculated, but instead it's interpolated from the background mesh on the overset mesh, which is why at this stage some trials have been made to investigate different interpolation methods, and it was observed that the cell volume weight method provided a smoother interpolation compared to the inverse distance method. These two methods are very similar. The main difference is that the cell volume weight method uses the overlapping volume of the background cell to the overset cell as the weight of the interpolation, while the inverse distance uses the distance from the background cells to the overset cells for the weight of the interpolation. But finally, the cell volume weight method was chosen, and the project continued by just simulating the ROV free to move with a uniform flow using the 6 degree of freedom rigid body motion solver of OpenFOAM. And at this stage, something interesting was observed. It was observed that the frequency of oscillation of the ROV matches the frequency of vortex shading, which is also known as the login regime. So after that, in order to finalize the simulation, we had to model the waves as well. So first, linear wave theory was implemented in MATLAB, and then by applying the boundary conditions to the computational domain, we could have a simulation capturing both the waves and the wave created by fixed structure. So after that, to capture the motion of the ROV at different operational conditions, the 2-dimensional number, the reduced velocity, and the Kulik and Carpenter number have been varied. I'm not gonna spend too much time explaining why these have been chosen, but these two basically have been chosen because they are the main governing dimensionless numbers for this system that was being simulated. And a brief summary of some results that have been found. So it was generally observed that at high Kc numbers, the lift coefficient and the other coefficients as well, like the drag coefficient, were higher. This was because at high Kc numbers, the period of the wave was large enough for vortex shedding to be developed, increasing the lift and drag coefficients, with one exception, the exception where with the low Kc number, but the reduced frequency of 2, which is shown right here. And this was because resonance was observed in this in that simulation. So in blue here we have the velocity of the ROV, and we see that it matches with the wave velocity, both in frequency, but it's also in phase as well. So this creates resonance and amplifies the oscillation of the ROV, which explains the outlier we had in the previous plot. Also, because we are interested in the dynamics of the ROV, the phase plots have been created, and we see that the ROV behaves differently for different degrees of freedom and different simulation cases. So for some simulation cases, the oscillations are composed out of only one frequency, which is why we get these elliptic shapes of the phase plots. While for other cases, we see that the oscillation is composed out of multiple harmonic frequencies. So the oscillations of the ROV are still periodic, but they contain more than one frequency. While for one case, it was observed that the oscillation of the ROV are quasi-periodic, which is why the phase plot does not have a specific pattern and seems quite chaotic. So basically, to conclude, this was the work that was done for my thesis. And now we're extending this work further when we're going to move on to the third objective, which is to try to develop a predictive model for the motion of the ROV under an environment where both waves and a fixed structure creating a wake are present, and try to implement that predictive model for an MPC control system within OpenFOAM. Yeah, thank you for your time.
Thanks, Nikitas. Very nice talk. So as usual, I request you to look into the chats, and if there are a few questions for your presentation, please answer them in the chat box for the interest of time. Thank you very much for joining. So now we request our next speaker, and our next speaker is Dr. Prabir, and he will be actually talking on the subject of enhancing heat transport in thermal convection, the role of surface roughness and partitions. Could you please share your screen?
Yes. Hello, sir.
Yeah, we can see.
The screen is visible?
Yes.
Okay.
All perfect. Thanks, Prabir. Okay. Please go ahead.
Okay. So thank you very much for giving me the opportunity to present my work. So I am Prabir. So I was working under Professor Rajaram Lakkaraju sir and Professor Prashant Kumar Das sir. So let's look into the discussion. So my work is on enhancing heat transport in thermal convection, the role of surface roughness and partitions. So here in the first picture, we can see that the bottom surface is heated. In that bottom surface, we can see the roughness in the form of rectangular base and triangular top. Okay, and in the top surface also, the top surface is cold and the roughness is same roughness, bottom rectangular base and triangular top. Side walls are adiabatic, and these blacks basically, these are basically strips indicates the partitions. So what we have done, we have varied these partition heights. So try to see how this partition height improves the overall heat transport of the system. So whenever we have varied this partition height, we found that the single large scale roll break down into 2, 3, 4 rolls, and finally multicellular state. So okay, so next look into the applications. So heat transfer between hot and cold fluid have a potential role in generating power. So next is how geothermal power plant works. So it has 5 components where in the geothermal reservoir where the hot water is there. So this is extracted through the production well, then it's converted to steam, and then it runs the turbine. After that, it transferred to cooling tower and condensed back, and the cold water is injected to the groundwater level through the injection well. So it has other applications like electronic cooling systems like printed circuit board heat sinks and heat pipes. So in nutshell, we can say that RV convection, Rayleigh-Bénard convections has applications like mantle convection, cooking or bubbly convections, mixing convection, complex geometries, solar power plants, and so on. So now let us look into the control parameters. So first one is the Rayleigh number, and Prandtl number is basically the fluid property and aspect ratio. And in response parameter, we found the Nusselt number, which is basically the dimensionless heat flux, and another is the Reynolds number. So several researchers has proposed different kind of scaling laws, like in 1954, Malthus proposed 1/3 scaling law. In 1962, Friesman proposed half scaling law. In 1989, Casting proposed 2/7 scaling law. Now the question is, which one is correct? So in 2004, Grossman and Dose gave us a direction, like he has divided the whole domain into 2 parts. One is bulk and another is boundary layer. So whenever the flow is bulk dominated, then we can see the scaling close to 0.44, and whenever this is boundary layer dominated, then we can found that the scaling close to 0.22. So that means we cannot randomly pump or pull water from the underground without deciding the location. Means we should have some kind of knowledge that in the underground what kind of flow pattern is that. If we have that kind of knowledge, then we can identify the locations from where we can drill and put the injection and production wells. Now let's look into the geometric configuration. So here I have generated this mesh using the block mesh, and here H is the enclosure height, H1 is the roughness height, and H2 is the height of the rectangular portion of the roughness element, and H3 is the gap between conduction plate and partition board. So this is the conservation of mass, momentum, and energy equation under Bossing's approximation. So now let's look into the flow pattern. Whenever we have varied the number of partitions, these are basic black strips are the basically partitions. These are adiabatic partitions. So we have varied these partitions, and how these partitions improve the overall heat transport and the changes the flow pattern, that we'll see in the animation. So here we can see that the single large scale roll using one partition, you can see that single large scale roll size of this roll reduces, and by increasing the number of partitions, we can found that the tip of the triangular portion of the protrusion act as an active plume emitting spot and alternate hot and cold channels, alternate hot and cold vertical channels we can see. So by increasing number of partitions, we can see that monotonic increase in overall heat transport compared to the classical square RV case, where there is no protrusion, no partition, only simple square cells, square RV cell where bottom surface is heated, top surface is cold. Next is what? So we have varied this partition height. So here this gap is 0.40 h, and with decrease in gap from 0.40 h to 0.001 h, we can found significant change in flow pattern. So we'll see the animation. So here single large scale roll break down into 3 rolls, 4 rolls, and then alternate hot and cold vertical channels, then finally multiple rolls stacked vertically. So here, with a decrease in gap from 0.40H, we found that the monotonic increase in overall heat transport or the Nusselt number, and at a specific gap or at an optimum gap, we found the maximum heat transport. Further decrease in gap, that means with further increase in the partition height, we found that the heat transport reduces and it reaches to a value which is lower than the classical square RV case. Next, we have shown the time average temperature and pressure field. So this is for gap is 0.01 H, for which we observe maximum heat transport. So this panel A for time average temperature field and panel B for time average pressure field. So in this case, in panel B, we see that this high and low pressure zone. This basically red basically indicates that high and blue basically low pressure zone. So alternate high and low pressure zone takes place. So due to that, fluid flows from a high to low pressure zone with high velocity, which reduces the thickness of the thermal boundary layer and improves the overall heat transport of the system. So next is NU versus RS scaling. So here we found that the scaling ranges between 0.27 to 0.34. So for this gap 0.01 H, we found up to Rayleigh number 10 to the power 7, the scaling exponent 0.38. So here we see in these each and individual vertical channel, hot plumes are rising, cold plumes are falling. So, but further increase in Rayleigh number, we found that these unidirectional motion of the thermal plume. So in one channel, it is hot plumes are rising and another channel cold plumes are falling. So, and complete wash out the cavity in between two consecutive roughness elements. So which improves the overall heat transport of the system. And you can see in this figure also. Next, look into the conclusion. So we found maximum heat flux enhancement in roughness with partition RB case approximately up to 2.7 times compared to classical square RB at an optimum gap in between conduction plate and partition board. Next one is the maximum heat transport enhancement is due to strong horizontal flow through the gap between conduction plate and partition board, which locally reduces the thickness of the thermal boundary layer and improves the overall heat transport of the system. Now let's look into the OpenFOAM. So in OpenFOAM, we see three directories. First one is 0. In 0, you can find U, P, and T. U for velocity, and where you can mention the initial and boundary condition. P for pressure, and T for temperature. In constant, you can find transport properties, which basically physical properties like viscosity, thermal diffusivity, and G for gravity. And in system, we found control dict, FV scheme, and FV solution. In control dict, the control the simulation run time, start time, end time. So these things, and FV scheme, this discretization scheme, and FV solution solver settings. So to run the simulation, we have to run the block mesh, then we can run the solver, buoyant Poissonic simple foam, and to visualize, we have used parafoam or paraview. So in OpenFOAM, there are other solvers which solve the heat transfer problem like buoyant Poissonic simple foam. In this solver, the buoyant turbulent flow of incompressible fluids with Poissonic approximation. But in buoyant Poissonic simple foam, here we use the same like a simple foam, but here we use the Pimple algorithm, which is merge of Piso and simple algorithm. And buoyant simple foam, a steady state solver for buoyant turbulent flow of compressible fluids, and buoyant pimple foam, a transient solver for buoyant turbulent flow of compressible fluid using Pimple algorithm, and heat transfer foam is a simple solver for heat conduction problem in solids. Now let's look into the buoyant Poissonic simple foam. In buoyant Poissonic simple foam, you'll find that buoyant Poissonic simple foam.c, this is the main source code, and then create field.h that creates the fields. U equation that solves the momentum equation, T equation solves the temperature equation, and P equation.h that is solves the pressure. This is solve the pressure, connects the momentum velocity according to the new pressure field, and adjusts the pressure level to obey overall mass continuity. So in this buoyant Poissonic simple foam.c, we'll find that has include CFD.h. So then single phase transport model.h, and these basically I'm not going into detail on that. So you can find the PPT, and that is well described, and it is in time loop and further Pimple pressure correction loop and references. And thank you. I'll be happy to if you have any questions or queries.
Thank you, Prabir. It was a nice talk. Could you please look into the chat box and answer the relevant queries on your talk?
Definitely, sir. Definitely.
Thank you. Thank you for sharing your work with us. So can we next invite our next speaker to actually try to turn on the cameras and sound. So our next speaker is Mr. Rakesh Kumar from IIT Kharagpur. Rakesh, are you here? Rakesh, are you here? If you are here, could you please turn on your camera and mic? Okay, in that case, while we wait for Rakesh, let us go for our next speaker, if he is present. Our next speaker was Mr. Pratyush Kumar from IIT Bombay.
Yes, sir, I am available. Hello?
Can you turn on your camera, please? Yes.
Yes, sir.
Yes. Okay. So while we wait for Rakesh, I request Dr. Pratyush Kumar to share his work with us. Could you please try to share your screen?
Yes, sir, 1 minute. Sir, is it visual?
Yes, we can see your screen and we can also hear you. So Dr. Pratyush Kumar is actually, I think, completed his PhD from the Mechanical Engineering IIT Bombay. And he was working with Professor Sandeep Kumar Saha and Professor Atul Sharma. So I request him to share his work with us. Thank you. Please go ahead.
Yes, sir. Good evening, sir. Am I audible?
Yes, we can hear you, see you, and we can also see your presentation.
Okay, sir. So, good evening to all of you. So, I am Pratyush Kumar, and today I am going to present a topic that is the modeling local thermal non-equilibrium heat transfer with the radiative effect considering the local porosity distribution using the OpenFOAM. So I did this project in my PhD work and under the guidance of Professor Sandeep Shah and Professor Atul Sharma from the IIT Bombay. So this is the agenda that I'm going to present. So first, I will give you some idea about my project. Then I will discuss about the available methodology to study the porous media as a packed bed. Then I will discuss about the governing equations and I will discuss about the numerical modeling inside the OpenFOAM and then validation and finally the applications. So speaking of the porous media as a packed bed, so this packed bed used in the various industrial applications like chemical, nuclear, thermal storage, and many other industrial applications. So to study the packed bed behavior, numerical studies are performed using the finite volume. And in that scenario, if you're taking it as a porous media, we add a source term into the governing equations, which account for the effect of the porosity in the governing equations. Various models are available in OpenFOAM, and these models generally consider the constant porosity in the different directions. So if you have a local porosity variation inside your CFD domain, so this you cannot take consideration. And if there is a wall effect, so like if you have a small thickness or a small width, so in such scenario, you cannot ignore the wall effect. So in such scenario, you have to consider the local porosity distribution. So that is where my development was lies. So speaking of the studying the packed bed, so generally three approaches are used. That is the porous media approach, CFD-DM approach, and experimental approach. So experimental, that is not something that is related to the present conference. So this CFD-DM approach, we actually create the model. We have a given canister, we fill the given canister. And after filling the particles, we create the geometry. And after creating the geometry, we do the meshing. And after that, we do the CFD simulations. So if you use OpenFOAM for meshing, you can adopt the snappyHexMesh and the cut cell method. And this porous media approach, we solve the given Navier-Stokes equations by adding a source term into the Navier-Stokes equations. And that source term account for the porosity effect, which is due to the filling of the particles inside a given geometry. Now, this both method has some pros and cons. Like in CFD-DM approach, is considered the microscopic behavior, but at the same time, it is time consuming and it requires the higher computational cost. And this porous media approach consider the microscopic behavior and the wall effect. Uh, at the same time, it will require the lesser computational cost, but it ignores the microscopic behavior. So based on the requirements, you can adopt which methods is suitable for you. So I have to study the parametric study. So that is why I have started with the porous media approach. So what we do in porous media approach, so this is the governing equations. In porous media approach, we add a source term, and this source term can be modeled using the different correlations. For example, so if you are adopting the Darcy-Forchamier coefficient model, so this Darcy-Forchamier coefficient model accounts for the viscous resistance and internal resistance due to the porosity. And this is the correlations for the this Darcy-Forchamier model. If you want to write this term in terms of the OpenFOAM, so this Darcy coefficient is written as the 1 by k, and this Fortier coefficient can be written as the CF by under root k. Okay, so this is something related to the mass and momentum conservation equations. Now, if you want to model the energy equation, there is a two approach you can model the energy equations. That is the LTE model, and second one is the LTNE model. So if the difference between the thermal conductivity between the solid and fluid is small, then you can adopt the LTE model. But if the difference is larger, then you have to adopt the fluid and LTNE model. Okay. So my study was related to the nuclear power plant. So the difference between the fluid and solid thermal conductivity was large. So I have to adopt the LTNE model. So in LTNE model, there is two different equations for the fluid and solid. And this two equation is coupled with the heat transfer coefficient between the solid and fluid. So this STS minus TG, and here STG minus TS is coupling between these two governing equations. Now at higher temperatures, in my study was focused on higher temperature, we have to consider the radiation heat flux also. So if we take a given packed bed, the heat transfer mechanism is very complex. There are different phenomenon is happening, there is a conduction between the solids, conduction between the gas in the voids, conduction between the contact area between the adjacent particles. So considering this different different heat transfer mechanism, different authors have proposed the different thermal conductivity, effective thermal conductivity of the solid and gas. So like I have used the JBS model because it is widely adopted in the literature. So this effective thermal conductivity model for the solid and gas consider most of this heat transfer mechanism inside the packed bed. Now to model the heat transfer coefficient between the solid and fluid, this Wakao model I have used because it is also widely used in the literature, and even in my lab while studying the thermal energy storage system, this model is adopted by many scholars in my lab. So I have also taken this H star. So as I stated that we cannot ignore the radiation heat flux at the higher temperature. So even to model the radiation heat transfer flux, we have two approaches. One approach, we can actually model the fourth order radiative transfer equation. And in second model, we can adopt the effective conduction approach. That is the conduction equation equivalent to the Fourier conduction law. Since inside a packed bed, it is a very complex domain. So to calculate the effective optical properties like emissivity, transmittivity, and other optical properties, this is a very hectic task if we want to adopt the first approach. So generally, it is recommended that we should go for the second approach, that is the effective conduction approach. So what we do in the effective conduction approach, we equivalent means we calculate the Q radiation equal to minus K radiation of the means this del T. Okay, so that is similar to the Fourier conduction law. Now this K radiation is the effective thermal conductivity due to the radiations that can be calculated from this correlation, and where F is known as the radiative exchange factor, which can be calculated from this BB correlations. So once you calculated this effective thermal conductivity due to the radiations, you can add this K radiation into the effective solid conductivity, because radiation is generally happens due to the solid particle, solid phase. So we can add this K radiation with the effective conduction due to the solid, and this K equivalent will be go as an input inside the this solid equation of the LTNE model. So this is all about the radiative heat transfer flux. Now, speaking of the numerical model, so as I told that we have to consider the heterogeneous porosity. So that is why I have taken this Darcy coefficient and Fotiou coefficient as the volume tensor field. So once you define it as a volume tensor field, you can define this porosity dependent quantities in each cells. So once you are able to define in each cells, you can locally define this D and F. So once this D and F is defined, you can calculate the force due to this porous terms, and this is how this force term, and you can see here that this is the Darcy force area equations that I have shown in the third slides. And once this force term is calculated, then you can calculate this update the U equations. So you can update the equations. So only in simple form you can find that this U equation minus grad P is written. Now this is additional term is taken as the dot product. But this U is only account for the momentum equations. Now you have to also solve for the continuity equations. So that is why this H by A is calculated. And once you what H by A is calculated, so rest you can do the pressure velocity coupling, which you can adopt from the any simple form kind of solver. So this is all about the Navier-Stokes equation and momentum equations. Now speaking of the LTNE model of energy equations, so I have again taken this Kg and Ks as a volume scalar field, where this temperature dependent properties has been updated during the runtime fluid and solid simulations. And using this Kg and Ks, this effective Kge and Kse effective will be calculated. And for radiation effect, this effective thermal conductivity due to the radiation is calculated using these correlations. And after calculating this Kr, you can add this term into the effective solid conductivity, and hence you can calculate the overall thermal conductivity of the solid. And this is one equation that I have stored for the solid phase only. Similar equation will be written for the fluid phase also. Only difference is that this Ks overall is account for the thermal conductivity, but there will be no radiation effect is taken consider in case of the gas thermal conductivity. So this is the solid phase, and another equation will be given for the fluid phase also. So this is all about the numerical development for the momentum and mass equations and the energy equations. Now validation part, I have validated first for the pressure drop validations. So I've taken a square duct of the length 10 mm and cross section 1 mm squares, where I've taken the porous medium of length around 0.05 mm. And in that porous medium phase, I have taken D and F as a function of the X directions. And I calculated analytically, and also I have compared with the numerical solver, and it is in a good agreement. And for the,
can you please conclude the results?
Yes, sir. For this is the last second slide. So this is the LTNE model I validated with the experimental result of this cited paper, and I considered the JBS and PB model. And you can see here that again this is the this is validation, and around 10% is maximum error, which has been adopted while validating with the experimental result. And these are the some application that I have done during my PhD work. So this work is related to the tritium bridal blanket concept, and this is the very high temperature reactor I have validated with this work I have done. So this work will take another 10-15 minutes if I want to explain. So just I am showing you the application of the developed solver I have shown in these slides. And with this, I would like to conclude, and thank you to all of you.
Thank you very much. It was really interesting talk. I request you to see if there are any relevant questions to your talk to answer, but I just want to make a comment that the source term that you are adding,
Yes, sir.
and in terms of Darcy and Forkmeier coefficients, they
Yes,
are
sir.
related to the permeability, right? That's what you
Yes, sir.
mean.
Yes, sir. Yes.
Because the porosity
So,
term should be included in terms of the Brinkman terms, which I
yes, sir.
think you are not including in the equations.
So, sir, actually, just I said that my focus is only related to the packed bed. So, the in packed bed, the Darcy and Forsheimer coefficient is a function of the porosity only. So, in Bejan paper, there is a correlation is given that how you by using the
Yes.
particle.
My point is, of course, porosity and permeability are
Yes, sir.
correlated. They have some empirical
Yes, sir. Sir.
relationship, but we cannot directly predict the porosity from permeability.
Yes, sir.
That
Yes, sir.
was
That
my
we
comment.
cannot do that.
All right. So I'm very curious about one thing. That's why I want to ask. You have implemented some variable permeability in your packed bed, right?
Yes,
So
sir.
can you define these Darcy coefficients as a
Yes, sir.
function of some parameter of the system, or you are specifying cell-specific values to these Darcy
Yes, sir. Yes,
coefficients?
sir. Yes, sir. So, sir, I have defined with the function of x, like you can you can take this coordinate dot x function and you can take the x value.
Okay, I got it. So it's a
Yes, sir.
parametric equation. So it's a
Yes, sir.
parametric function.
Yes, sir. Yes, sir.
All right.
So
Thank you.
I have assumed
Yes.
as a polynomial equations, and using that polynomial equations, I have defined in the differentials.
Okay. Good.
Yes, sir.
I got it. So could you please look into the chats?
Yes,
I
yes,
took
sir,
the
of course.
privilege to ask you the questions, and sorry to the audience, but we don't have enough time. So please look into the chat. If there are any questions, please answer them. Thank you
Okay, sir.
again. So I
Thank you, sir. Thank
now
you very much.
invite our next speaker, Rakesh Kumar from IIT Kharagpur. Could you please try to share your screen?
Yes.
Can you hear us? We can't hear you. No, sorry, we can't hear you actually.
Yes, sir.
Can you try to change your speaker in the Teams? I mean, yes, so exactly.
Then we can start.
I think once the time you take to figure out this, let's take a short break of 10 minutes, and then we come back and you will be the first speaker.
Yes, sir. I can